Welcome back, everyone. You're watching Centerline Designs. My name's Cole, and today we're going to be doing a video on how to AC TIG welding aluminum. I want to take you through start to finish. If you have no experience with this, I want to get you going, help you get started. It's not that difficult. We're going to go through everything from tungsten selection, setting up your torch, to the base material prep, machine settings, gas flows, and I'd like to do some passes, show you what the good weld should look like and what some not good welds look like. Like if you have poor shielding gas or improper machine setup, things like that. It might help you troubleshoot when you're getting started. If you're not getting the results you want, we'll be able to compare to what I'm doing here, and hopefully that'll help you get on the right path. So with that being said, let's get started. So today, the welder we're going to be using is the Firstis CT2050 provided by YesWelder. I've been doing quite a few videos on it already through various different builds. I'm really liking the machine. It's the machine today I'm going to show you how to get the settings set up on. But all the other parts as far as tungstens, torch setup, gas, material prep is all going to be the same no matter what machine you have. So really the only specifics come to the actual user menu on the machine. With that being said, let's get started with the tungsten. If you're new to TIG welding, tungsten is the electrode that's used to transfer the arc between the TIG torch and your workpiece, the base metal. In this case, it's going to be aluminum. And there's many different types of tungstens out there. The two common types that I'm always going to for AC TIG welding and also DC, because these two can be used for either or, is a 1.5 or 2% laminated tungsten, which I think is often gray. I've seen the color codes not be consistent, so I'm not going to go too much on the color code. I'm really just going to go on the type of tungsten. So a 1.5% or 2% laminated is my go-to tungsten. I use it probably 90% of the time. It has great arc characteristics. It's easy to use and it's very versatile. So that's my primary go-to. The next would be serrated. Serrated I've found is a little bit better when you're getting into thinner materials or when I've had to do welding on contaminated aluminum, like cast aluminums, or I did some welding on a boat before where my laminated was not working for me. I couldn't get the weld that I wanted to achieve. So the first thing I try swapping out is my tungsten because it's super easy, and swapping out the tungsten fixed the issue for me. The next part is the nozzle you're using. So today we're going to be using a 332 tungstens. You can get them in a variety of sizes, 1/16 of an inch, 332, 1/8, and generally the larger tungsten has a higher current carrying capacity. But for a machine like this, I really doubt you'd ever need to go to a 1/8. That would be the low end of that size. 332 is what I primarily do most of my welding with. I don't often go too thin. I usually stay within about 1/8 to 1/4 inch material, sometimes 3/8, and sometimes 1/16 of an inch or a little thinner. But like I said, today we're going to be using a 332 laminated tungsten. Pull it out of the torch here. It's held in by a collet and a collet body, and then there's the nozzle, and the shielding gas comes through the torch and out through the nozzle. And it's all about having shielding gas coverage around your tungsten, because the tungsten does not want to be exposed to atmosphere. It will get contaminated as well. So when you're grinding your tungsten, you always want to be grinding it so that the grind lines are parallel to the length of the tungsten itself. If you're grinding it sideways on your grindstone, you're going to get swirled grind lines, which is really going to mess up the arc. And it's all about having a really good quality arc to get a really nice weld. You always want to be using a dedicated grindstone. Preferably, if you can get one, get a tungsten grinder. I've seen them on YesWelder's site, and I'm going to have to talk to them about getting one because I'm very, very interested. I didn't know they offered it, and I'm very curious. The advantage of using a dedicated stone is that you don't put contaminants into the tungsten. When you're welding aluminum, it's all about clean, clean, and clean. You want to have as little contaminants, and every step of the process is about getting those contaminants out of there. So dedicated stone, grind with parallel to the tungsten itself. And if you're using, different size tungstens, I always grind my taper to about 2 to 3 times the diameter of my tungsten itself. So if I'm using 332, I would be going with about a 3/16 taper, and I have always used a slightly blunted point. I go to a complete point when I'm DC tigging. On AC TIG, I like a slight blunt. It helps get that nice arc. So next comes nozzle selection. This can be determined by a variety of factors. I've found that 332, what am I using? A number 6 nozzle is really nice. If you go too wide with your nozzle, the cleaning action of the AC square wave or sine wave will widen out and etch your material a little more. So if you're really wanting to have a nice clean weld with very little etching on either side of the bead, you want to pull that shielding gas coverage in a little tighter, and that's what a smaller nozzle is going to do. So as you decrease your tungsten size, you want to shrink your nozzle, and as you increase your tungsten size, you want to increase your nozzle size. And this is all specific to aluminum welding. The one thing you won't be using is these Pyrex nozzles you typically see with welding stainless, because when you're doing stainless, you want a very wide gas coverage. You're DC tigging, it's a whole other ball game. So again, if you're just getting started, don't think too hard about it. You're using 332, go with number 6. If you're using 1/16 of an inch, you can probably get away with number 5, maybe even a number 4. That's getting pretty small, and vice versa. If you go to 1/8, you can go up to a number 7 or a number 8 nozzle size. It's really up to you. So I'm just going to try and teach you here, show you what good results look like, help you get set up, and then you have your back cap. And when you're doing all this, you want to make sure that everything is nice and tight in here. If you leave things loose or the O-rings are messed up and you're letting contaminate, the atmosphere, into your weld, you're going to see it. It's going to be dramatic with aluminum. And I think that probably covers enough to get you going on torch setup. The other thing I suggest, if you're getting new to AC TIG welding and you're getting a setup, go ahead, and most manufacturers, YesWelder has a really nice consumable kit. It came with a variety of nozzles, back caps, collets, the collet bodies that go inside the torch itself, and diffusers. There's a whole beautiful setup here. It's going to take the guesswork out of it. Just go order a kit. They're not that expensive, and it will get you going really quickly. I really like this kit. Now that we've covered the basis of getting your torch set up for AC TIG welding, which didn't take too much, it's not that much different, let's talk about the base metal, the aluminum itself. Okay, so let's talk about the base metal, the aluminum we're going to be using today. I have cut up a bunch of coupons of 5052 1/8 plate aluminum, or sheet, whatever you want to call it. And with that, we are going to be using a 5356 filler rod. A good rule of thumb with filler rod selection for diameters is you pretty much can choose a filler rod with a similar diameter of your tungsten. The only other rod I typically use is a 4043 filler rod, which I use for more aluminum alloys like castings, outboard bottom ends, engine casings, different things like that. It helps blend in all the impurities. But again, if you're just getting started and you're using nice new clean aluminum, 5356, go get yourself some rods. So there's an interesting part about aluminum is that the surface of the aluminum develops an oxide layer, and this is what is going to fight us the most. Just like steel rusts or oxidizes, aluminum builds an oxide layer as well over time. That oxide layer, the reason it's causing us so much problem is because it melts at a significantly higher temperature than the base metal itself. So you can imagine striking an arc on here and trying to develop a nice little molten puddle that you can feed rod into. If that oxide layer is really thick, which it just builds and builds over time, you're going to have to put a lot more current or heat into that part to try and get that puddle formed, because you have to burn through that oxide layer to get to the molten aluminum underneath. And that often causes issues, because as you're trying to, get a butt joint or any kind of weld, as you're trying to get that puddle joined between the two parts, it kind of wants to repel itself. The oxide sort of separates it. It holds impurities in it. And what can happen on thinner metals is you're trying to heat it up to get a puddle formed, and the actual base metal heats up so much that it just drops right out and you'll be left with a big crater. So what I always suggest if you're doing anything with aluminum, just keep remembering clean, clean, and clean. I can't stress that enough. Get yourself a dedicated wire brush, right on it, aluminum, and you want to go ahead, wire brush that oxide layer off. Just scratch it up, and then when you've done that, go ahead with a nice clean rag and some acetone wipe off all of that oxide dust and any oils that would be on there, and then you have a nice, clean, exposed, bare aluminum. And when you strike that arc, it's gonna puddle up really quickly, it's gonna fuse to the other part. And when you add filler, which I also suggest wiping down with acetone, you'll see why, it will just blend in really easily and your puddle's gonna flow really good. So the other thing I wanna talk about with aluminum, we're using AC to weld with and not DC like most other types of welding. And the reason we're using AC is a sine wave. It's got a positive half cycle and a negative half cycle. In the positive half cycle, the electrons are coming out of the part to the tungsten, and what that's doing is burning off or cleaning that oxide layer. And the negative half cycle is moving electrons back into the part, which puts heat into the base metal, creating your weld puddle. So we have an adjustment on the welder called balance. And balance is adjusting in one cycle of a sine wave or a square wave. If it was a typical wave, it would be 50%. The same amount of positive time is the same amount of negative time. Balance adjusts that. So it doesn't change the length of the wave. Changing the length of the wave would be adjusting the frequency. Let's just consider us using the same frequency. So the wave stays the same length, but the negative and positive half cycle, we can change that duration. So that's effectively changing your cleaning action. With nice clean aluminum like this, we're probably going to be using a balance setting of around 30%. What that means is on your waveform, the positive or the EP, electrode positive, will be only 30% of the total waveform, leaving the other 70% EN, electrode negative. So 30% of that wave is going to be cleaning the aluminum and 70% is going to be welding the aluminum. If you got into more contaminated materials like castings or different things like that, you can adjust that balance up so you have more cleaning action and less welding. So you might say, well, why don't you just set it high and forget about it? The reason you're going to do that is, again, it has to do with that electron flow. To have a nice, efficient welding, you want to be putting all the heat into the part and ideally very little into the torch. It's going to get your puddle faster and it's going to allow you to move quicker, so you weld faster. I mean, it's all about efficiency. The other issue is if you crank the balance too high, as I said, the electrons are coming out of the part into the tungsten. What that's going to do is overheat your tungsten. Tungsten is really good at operating at high temperatures, which is why we're using it as an electrode, but it can only handle so much current and so much heat before it just melts out. So it's always best to try and find the balance that's going to work best for you. And it's really trial and error. I mean, start low, turn it up. You'll notice that you're not getting much weld happening and your torch is overheating, which is also, I guess, brings me to the next point. If you're welding with too much balance, the limiting factor of a air-cooled torch like this in an inverter-based machine is going to be your torch. This is going to overheat, which is going to bring down your duty cycle, which is the amount of time you can weld for before you have to let the machine cool down. Something else I should mention when playing with the balance of your machine is that it's not only playing with the cleaning cycle and where the heat's going in the part, it's also going to affect your penetration. And that's one of the reasons why you also want to try and find the right balance. When you set your balance low, which is very little cleaning action, like 10, 20, 30%, you're going to concentrate that heat to a smaller area in your base metal, which is going to allow you to get probably a faster puddle, but penetrate more. So you can wind up getting a stronger weld when you crank that cleaning action up 50, 60, 70%, if you ever need to go that high, if it does go that high. That arc is spreading out and you're doing more of just heating the part than actually trying to get a good penetrating weld. And that's another reason why you just don't want to crank the balance up. You really want to try and dial that in. And it's going to take practice. It's going to take some learning and experience, but you'll get there. It's just one of those things. I guess the other thing to talk about, I might as well do it right now. We're talking about balance of that waveform and shifting that center point. The other thing is the length of the wave itself. If you shorten the time span in one cycle, your frequency is going higher. Frequency is hertz. I guess, let me tell you what we're going to be welding with first. Typical aluminum like this, we're going to be setting a frequency between 85 and 100 hertz. And you'll be able to hear that frequency change. If you need to weld thinner metal and you want to get a good amount of cleaning action, you're probably going to want to go up to a higher frequency because every cycle happens that much faster, which means you can move along a little quicker before you saturate your part with heat. I often don't play around with frequency too much. I typically weld kind of the same things. So it's something you can go ahead and play with yourself, but that adjustment is there. And if you want to learn more about it, go ahead and research a little bit on your own, but 85 to 100 hertz is where we're going to set this. All right, since we're talking about base metal and we've talked a little about filler rods, as I said before, when you're wiping your parts and stuff down with acetone, which is a safe chemical to use, safe solvent, it evaporates off really quickly with no residues and it's not going to harm you through welding processes. You're not supposed to use brake cleaner or things like that. It can, when exposed to arc, if it hasn't fully evaporated, it can create some very toxic gases which can really hurt your lungs. The other thing is wipe your filler rods down with acetone because they get oxide on it too. You can even take a Scotch-Brite pad if you feel you have some heavy oxide on your filler rods and just run them through, wipe them with acetone, and it's just going to help you achieve that weld you're looking for. The other thing I suggest is have a really nice clean pair of TIG gloves. TIG gloves are thick enough that, you know, they shield you from some of the heat, but they're thin enough that you can feel the filler rod. And again, clean, since you're handling all your material. If these were soaked in dirty oil or have carbon steel rust or different things on it, it's just going to contaminate that weld. And at first, I mean, you can hold the rod however you want and try dabbing in, but something to practice is feeding the rod with one hand. And it's a bit of a hard thing to learn, but when you set up, because one of the other things I'm going to talk about when you're welding is being comfortable. And when you're TIG welding, comfort is going to be a huge factor in you getting that weld quality you want. So, you know, test your weld passes, get comfortable, take a breath, and then when you're feeding that rod, if you're moving your hand all the time, you're going to push in too much, you're going to pull away. The other thing you want to do is always try and keep that tip of your rod close to your TIG torch. You want to keep it in that shielding gas, because if you feed your puddle, pull the rod out, that oxidizes, and then you feed it in again. So you really want to hold it close, get stable, and learn how to feed a rod with one hand. That is definitely something I suggest being able to learn. The other thing I'm going to mention is, if you're new to this, I mean, this video alone isn't going to teach you everything you need to know. I'm not an expert, I guess you could say. I'm self-taught, although I've been doing this for 15 years. I've researched a lot, I've talked to a lot of experts, so I do feel I have a pretty good understanding of what I'm doing. But YesWelder's manual for the CT2050 has some really good resources in it. I printed it out myself just to make sure that I'm trying to cover all the topics I should cover. So try and use some of those resources. I mean, most people probably haven't opened the manual to their own machine, but it gives a great breakdown of what all the components are called in your torch. It breaks down the balance, the frequency, your pre-gas, post-gas, ramp currents, all that type of stuff. So take a read on that as well. It's going to take kind of exposing yourself to it several times to really start to understand what that all means. Okay, with that being said, let's go ahead and start talking about some machine settings, what they mean, and you know why you're going to adjust them. The machines typically have some default settings that are kind of in that range to get you going, and then you dial them in as you're trying to achieve that weld you're looking for. Other than the basic setting, which any welder, if you're TIG welding, you've probably done some other forms of welding before, is current. We're going to set the main welding current on the front face of the machine, and then I'll be using a foot pedal today. I really suggest when you're doing any TIGging, get a foot pedal. It's just going to help you out that much more. It's all a part of being comfortable. So Your main current, that's going to be pretty easy to understand. If we're doing 1/8 material, I'm going to set that machine to about 180 amps, which may be a little bit above where I'm actually welding. And then that foot pedal, I'm going to dial in the current because I'm going to ramp up high to get my puddle started. But then as the base metal starts to warm up and my puddle's established, I'll back off the current a little bit so that I can get a nice puddle that flows and we'll have a really good bead. One of the other settings you're going to see come up on here is pre-gas. What pre-gas is the amount of time between when you initiate an arc start on the machine, it's going to flow gas through your torch and then the arc will start. And that's to ensure that you have argon. In this case, since we're welding aluminum, we're using 100% pure argon. It's going to ensure that when that arc fires and starts, it's doing it inside the shielding gas, in an inert environment. So one of the things I suggest, if you haven't used the machine in a while, before you even start an arc, hold your torch away, strike it, listen for some gas flow, and purge any atmosphere out of your torch lead. So pre-gas, I was doing some reading. It's typically around 1/3 of a second. If you have purged your torch, that's going to be enough. It's going to get gas flow, the arc's going to start, and then you're going to be welding. Some of the other machine settings here, other than pre-gas, which we just talked about, are going to be the initial starting current, which again, I don't believe you're probably going to have to play with for now. That starting current is just the amount of current it's going to take to get that arc fired. If you're welding really thin material or maybe having a hard arc starting, you may want to turn it up or turn it down depending on what you're doing. The other adjustment the machine has is the current ramp time, how fast it's going to go from that arc start current to your actual working current. That is going to have preset settings. I'll show them to you. The actual flow rate of argon we're going to be using today, a good rule of thumb is CFH, I believe it is. Set it to twice your nozzle size. So if we're using a number 6 nozzle, we're going to dial our argon flow into about 12 to 15 CFH. If you're using a smaller nozzle, you need less gas flow. If you're using a large Pyrex cup welding stainless, you're going to need a ton of gas flow to cover all of that metal and the weld puddle. So again, that's something, 2 times your nozzle size is a good place to start. The next setting on the machine is going to be the opposite of your ramp up currents. It's your ramp down currents. We'll show you the demonstration on the user panel here. I'm not convinced I'm going to play with any of that, but one thing you're going to want to know about and probably need to adjust from time to time is post-gas. Post-gas to me is fairly important because it all has to do with not contaminating your tungsten or your part. If your gas shut off right when you stop your current flow, you're going to still have molten aluminum that then becomes exposed to atmosphere and contaminates. Your tungsten is going to be glowing red hot and immediately get exposed to atmosphere, which is going to contaminate it. So post-gas, I think I was reading in the manual on this machine is default to 2-3 seconds. That's really going to be dependent on your base metal and your tungsten size. A smaller tungsten and smaller base material is going to cool down quicker, which needs less post-gas flow to let everything cool down to the point that it won't get contaminated when the gas is removed. As you go up in base metal thickness and tungsten diameters, like going to 3/8 material or a 1/8 tungsten, all those components are going to hold heat longer, which means you're going to need more post-gas flow to cool the tungsten down, let your weld puddle solidify before that atmosphere comes bombarding everything. It's all about trying to find a nice optimization there. But there's definitely some good settings to get started with. Something this machine can probably help teach you with is it has, smart settings. You can tell it aluminum and the thickness, and it has already preset settings for pre-gas, current ramps, post-gas, frequency, balance. It will do all that in there for you, but that doesn't mean you shouldn't understand the settings yourself. That's been a lot of talking. So I think we're at the point where let's fire this up, power it up. We'll go through the menu on this machine and let's start laying some beads. I want to get some nice close-ups. I'll describe the step of establishing your weld puddle and moving the bead along and dabbing in your filler rod. So I think we're ready. Let's fire it up. All right, so I was talking to you about argon flow. Now, the one thing you want to do is set this while the gas is flowing. And as you can see, that's at about 15, so I'll dial it back just a bit. I don't quite need that much. And that's pretty good. Okay, so this video is, gonna be specific on this YesWelder CT2050, but a lot of these settings are gonna be similar to any other machine out on the market. This welder here, you select the weld mode, AC TIG, DC TIG, stick, cut, cut com, and then here is your torch modes. So 2T is your button on your torch, because this one has a torch button. 2T is momentary, so the arc is only established while the button is being held. 4T is push on and then push off, and then foot pedal, well, I think that's pretty explanatory. Then some of the other settings you can go through. As you can see here, input line voltage is 233 volts. The machine right now is set at 45 amps, which we're going to be using significantly higher than that. I'll be setting to about 180. And then if you push the button here is where we're going to go through the slope down, eye stop, post gas, balance, frequency. So we're going to get to pre-gas. So I'm going to leave it set at about half a second. Starting current is 15 amps. If you are welding really thin material, you may need to lower that. If you're having a hard arc start on materials potentially thicker, oops, I guess it goes through the menu. Let's get back to I start. You could turn that up. Okay, so here are all the settings the machine has. As we talked about before, we have pre-gas. We can turn that down. We can turn it up. I'm gonna leave it at about half a second because that's a good start. I start, when I clicked on this initially, was set at 15 amps. That's a default. Now I have noticed that the pedal is more sensitive than what I was used to. So since we're welding thicker, well, not thicker, but welding 1/8, I'm gonna turn that up to about 30 amps. And that should bring the effective control zone of my pedal closer together. Slope up is 0 seconds, okay? So it's gonna go from starting current to full adjustment. We have our operating current at 180 amps, which again is fully adjustable through the foot pedal. Then we have slope down set at 0 seconds. If you wanted to ramp down and help crater fill, you could adjust that, because as you slow down your current drop, it helps to fill the crater in on your molten aluminum. Let's get back in there. I stop is 30 amp, or 15 amp, sorry. So I want to set that to 30 as well. We can play with some of these settings and see what they change. Post gas set to 4.5 seconds. I'm going to leave that there and determine on my own whether or not I have enough gas coverage at the end of my weld so that it's not contaminating the tungsten or the aluminum, and we'll go back and adjust post gas if we need to. All right, let's get back into the menu. Balance, as I said, set to 35. Let's turn that down to 30%. I think will be a good start for the clean aluminum we're welding with. And frequency, we'll set to 100. As I said before, 85 to 100 hertz is a really good place to be welding with your typical aluminums. It can go all the way up to 250 hertz, which is absolutely wild. That is a very high frequency. I've never welded at 250 hertz, but I guess there's a need to do it. So, let's get back in here. All right, hertz, let's get that back down to 100. I like 100. And put our current back to 180. So there you go. If you want to go through all the manual settings, that's how you do it on here. You adjust your pre-gas, your starting current, your slopes times, your welding currents, your stop currents, your post-gas, which is an important one in my opinion. Balance is also very important. And frequency is as well, but I find I don't often play with hertz that much. So the other thing we can do is let's go check out this smart feature on the 2050. Okay, so to get the smart feature enabled, let's hit AC TIG Smart. That lights up all of our other side of the menu here. So we have everything from 18 gauge, 16 gauge, 14, 1/8, 3/16. And the weld position. If you're welding flat, vertical, or overhead, it's gonna adjust the currents. And see, there you go. We're at 3/16 and it picked up the stop current. Post gas, it did increase as well. Balance is 30, which is good, 85 hertz. Pre-gas, starting current, and weld currents. And as we cycle through your different weld positions, it goes ahead and adjusts all the parameters to have the optimum weld for the given thickness of material and weld position you're welding in. Now, because I've done this for a lot of time, I really just prefer on setting everything myself. But if you're new to it, hit the Smart TIG, let the machine preset the values for you, and then once you get comfortable with the actual process of welding, then go in and start playing with things yourself. Don't let this overwhelm you. It's one of those things, you really just have to get in there and play with it. So I think that covers most of the settings. Again, we're gonna only be using AC TIG welding in this video. If you wanna go through and see, you know, some of the other settings that this machine offers, go ahead, but this is a AC TIG welding video. So I think we pretty much got it set up. Let's go over to the table and get some welding done. The first weld we're gonna do is just a simple butt weld. And if you've noticed, what I did was space my two weld coupons off this table. This is a 1/2 inch thick steel table. If I laid those down right on there, it's gonna really pull heat out of the weld joint right where they meet, and it can give you a little problems trying to get the molten puddle and the penetration you need. So I'm just gonna space that up a little bit. I'm gonna go ahead, I'm gonna tack the start and the finish, and then I'm gonna get in here and lay a bead down. As before, probably one of the things that will let you be the most successful is being comfortable. If you're in a very awkward position when you're trying to TIG weld because you're using 3 limbs at once, a foot and 2 hands, you're gonna be shaky. If you're trying to freehand your torch and your rod, you're gonna be all over the map, and wherever that torch goes, it's gonna put a weld puddle. So if you're looking for that nice, beautiful, straight stack of dimes weld, you need to be unbelievably consistent and stable. So always practice the movement through the whole weld first, then you know you're clear, start to finish. Your filler rod's not gonna hit anything, your TIG torch is loose enough. All these little things seem like they might be areas to skip and not do, but if you're trying to weld those picture perfect welds, it is all these little steps that are gonna, you know, separate the home DIYer ugly looking weld versus the professional. Okay, let's go ahead. Let's lay a bead down on this and see how it does, and then we'll start talking about the actual procedure of this, and hopefully I can get this camera set up and show you some real close-up action of it. All right, I'll show you there. I'll show you there. The machine can weld really nice. If you notice the backside though, very little penetration. And I do believe that was largely to do with this table. Even though I got a molten puddle on top, the bottom side of that aluminum was getting all of its heat stripped away. So I want to go ahead, stack this off, and let's keep going, and I'll show you what that penetration on the backside should look like. All right, so first thing I already noticed from that, I felt like I was getting it approximately the same amount of current, but the weld flattened down, which means it was sinking in more, penetrating a bit more. And I'll show you here, it's really hot, but you could see I was starting to see that penetration come through the backside. So again, that right there shows you that's something you gotta pay attention to. You gotta pay attention to the material you're welding on and how much heat it's pulling away from your part. But not too bad. And as a beginner, don't just try and focus on having a good looking weld. I find a lot of people do that. They're trying to create the perfect looking weld. What you should really be focusing on is a good quality, strong weld. So as a beginner, please, I mean, it's something to work towards making it strong and nice looking, but focus on the penetration and the quality of the weld over the look. All right, with that first piece done, I'm gonna go ahead and try and rig up this GoPro so that you can see, and I wanna walk you through starting the puddle, showing you the texture change. Since aluminum doesn't change colors, it changes textures, and that's the best way I can describe it. Hopefully you can see what I'm talking about, and then we'll go through the step of moving the torch, adding a little filler, letting it blend in, moving, adding, and that's all it is. You just work your way down the joint. We're gonna go ahead, get the arc started. When you're running at low current, you're gonna see the arc's a little bit erratic until you get the current up to a nice operating range, and then your arc will really start to become more stable, and it's gonna wanna go to one side of the part or the other. So we're gonna go ahead, get this arc established, get a puddle established. Sometimes I need to dab a little filler in to help the puddle, but then once we got it there, we're gonna hold that puddle for a second, let the part warm up, and then we're gonna move the puddle along. All right, I hope you can see that. Starting to get both sides melted a little bit. Dab a little filler in, there we go. Now we have a puddle. And I hope you can hear me over the buzzing, but we can hold that puddle here indefinitely. That is the beautiful thing about TIG welding. I can back that current off, and you'll see the texture start to solidify, or I can bring that current back in. We'll get that puddle, and if you can see what I mean, it's a texture change. Now we have a little bit of a keyhole happening. We're gonna go ahead, dab it in, and then move over a little bit. We're gonna let both sides melt in, keyhole, and dab it. And that is basically all we're gonna keep doing. You wanna watch that material flow in, and you're just adding enough filler to help the puddle. There we go. Move over about 1/8 of an inch, form a new puddle, dab some filler. And you can see there, I hope, I didn't crater fill. We wound up getting a pretty good crater. Okay, I'll talk you through this part here. So, that was the beginning. Again, not real uniform. I was concentrating on talking more than I was welding, but we crater filled that first bead, and I didn't crater fill the second bead. And that crater, ow, part's really hot. The reason you want to crater fill is if you leave a crater there, that is a great spot for a crack to form. So you want to ramp down your current a little slowly with your foot pedal and dab just a little filler and fill that crater in. And as you can see here, we were getting wonderful penetration, and I know it doesn't look, it looks like two separate kind of pieces still, but that's only because the backside wasn't wire brushed, so that oxide layer is making it look like it doesn't really want to fuse together, but that is 100% penetration right there. Okay, now that I've demonstrated establishing a weld puddle, holding the puddle, letting it keyhole penetrate, dabbing some filler in and moving that weld puddle along. I think that gives you the idea of doing a bead yourselves. So let's get into playing with some machine settings and seeing the results. I think one of the first settings we should play with here on this coupon is balance. I'm gonna show you either extreme. Let's turn balance way down, very little cleaning action, and then let's turn it way up and let's see the results. Hopefully we can see the etching differences on the cleaning action, and then I'm most likely gonna burn this tungsten up. So let's go ahead and do that and see the results. Okay, for this first demonstration here, let's go to balance and let's turn that down to 10. So right away I'm noticing a little bit more contaminant on top of the weld bead here. And I can also feel with my foot pedal that it's taking much less current to operate. Okay, that was not very pretty. Now let's set balance to 30%. We'll put a nice bead in the center and then we'll go real high. %30 is a nice setting. Let's test that out. The other thing I'm noticing is that tungsten now has no discoloration on it. So because we're using a really low balance and putting a lot of heat into the workpiece and not the tungsten, our post-gas flow is probably more than we need now, but it's keeping our tungsten from getting contaminated. All right, let's start a new bead and try this out. All right, so right away I can tell that bead is shinier. There is a lot less contaminant floating on the top. Significant difference. Okay, let's turn it up even higher. Let's go to 50%, which 50% for a material like this is really, really high, but I want to show you. Oh, I can hear the difference. Oh yeah, I'm needing much more current. The tungsten is balling up more than it ever has because again, I'm putting way more heat into the tungsten. So it's probably a hard thing to show here, but that tungsten got a lot hotter. It actually balled up really nicely, but I probably would need more post-gas flow. All right, now that we got that first test done with the balance, let's take a look at the results here. As you can see, we're running with 10% balance, and that is not what I would be looking for. The etching zone around the weld is almost non-existent, which happens from cleaning, the positive half cycle. There's a lot of contaminants, as you can see, on top of the weld puddle itself, because they weren't getting removed, they were merely just floating up to the surface. So 10% with this material is too low for my liking, so I don't like that. 30%, as you can see, there's a bit of a difference here. You see that white etching zone? That is the cleaning action taking place, and I'm quite happy with that. For what I do, I'm usually not worried about too much cleaning. I'm usually welding to get, a good weld. And also make it pretty. Now, mind you, these aren't the nicest welds in the world. My comfort level isn't as high as it would be because I'm trying to talk and video and do different things, but we're not really trying to look at the prettiness of this weld. We're trying to look at the difference that balance has. So as you can see, lots of nice cleaning action comes in. The actual weld itself gets rid of all of this black contaminant. The cleaning action got rid of that for us. I have more cleaning action to the top, which could be related to my torch angle. I probably should have my torch tipped towards myself a little bit more, which would have brought the arc and the cleaning action to the bottom, but it is still there and I'm happy with that. 30% is a nice, no pun intended, but balance between putting heat into the part and getting enough required cleaning. Now here is 50%, and the balance does go higher than that. The actual effective cleaning zone didn't get much larger, so I think we were probably maxed out to the shielding gas coverage we had. If you wanted this etching to come out even farther, like out to here, which there's not really a big reason to, the cleaning action will only take place inside of the argon shielding gas. So I probably didn't have much gas coming down over here because of the size of the nozzle I was using. So that just shows you how nozzle size does play a role in cleaning action. But effectively, between weld to weld, there isn't a lot of difference. I didn't really crater fill this, so you can see that little hole there is the crater we're talking about when you finish a weld. The best way to fill that is to slowly ramp down the current with your foot pedal while giving it just a little bit of an extra dab of filler rod at the end. Let the puddle fill in, because that little crater there can very easily lead to a crack migrating down the weld. And here I did crater fill it. So there's a little bit of a difference. I hope that explains what balance is and the effect of adjusting that balance. I think the next thing to show you is let's look at frequency. I don't really adjust frequency a lot. Like I said, I usually run between 85 to 100 Hertz, but just as a nice thing to show you, let's do the same thing as the balance. I'm gonna start really low, I'm gonna go to where I like it, and then I'm gonna go really high. I'm gonna go ahead, do all three of those. I'm not gonna try a video at a close-up. I'm not sure you're gonna see any difference happening there, but I'll get those 3 beads laid and then I'll bring you back in and let's look at the effective difference between those settings. Let's get some welding done and I'm gonna play with the frequency or the hertz. Okay, here's the coupon that we were playing with frequency. As I thought, and it's hard to show you here, there's very little difference in the look of these welds. Penetration varied. I wasn't really paying too much attention to that, so I can't really, you know, make a comment on penetration versus frequency. But what you could really tell was the sound. 50, 100, and 200 Hertz. You could definitely hear the difference in those welds. And my understanding is that as you go to higher frequency, that allows you to weld on thinner materials. You get more cleaning cycles, and it should penetrate a little bit better. All right, well, I showed you what changing the frequency did there. Really, you can hear the difference between 50, 100, and 200 Hertz. If you do any research on adjusting the frequency when AC TIG welding, it really has to do with adjusting your arc and the width of your puddle and everything like that. I didn't see a ton of that happen here, but that is what frequency adjustment is for. A lower frequency like 50 Hertz is going to create more heat into your part. The arc widens out. And as you go to higher frequency, it's gonna really tighten that arc up, bring it much into a tighter bead. And so if you're trying to weld some really thin material, you're probably gonna be going to a higher frequency. But there's the reason they say, you know, 85 to 100 Hertz is really where you wanna be most of the time. And as a beginner, just set it there and don't think too much about that. Frequency is not a setting you're gonna need to adjust very much. Then another thing we'll get into after this is playing with the pulse settings, because this is a AC/DC TIG, but also AC/DC pulse TIG, which means when you're welding that puddle, it's not gonna be just a steady arc. It's gonna cycle on and then back off to a really low current just to maintain the arc, and then pulse, go up to operating current and pull back. Go up to operating current and pull back. And the idea of that is to limit how much heat you're putting into your base material. And this can be critical. If you're welding on some components that you really don't want to overheat because it might warp the part or disfigure the shape or something like that, pulse welding lets you get the penetration and the weld completed with as little heat into the base material as possible. Usually it would be something you use when you're trying to weld thin metals and lay a bead on a really, really thin piece of aluminum, because you're not putting any extra heat in. It's not something I do a lot of. Pulse settings are really simple. The only thing to it is the pulses per minute that you're gonna have. And when you're running a pulse with a TIG, just talk about it now, it's gonna pulse on, and when it's pulsed on, you dab your filler rod when it's real hot, and then the pulse is gonna back off, and that's when you move the torch. And then the pulse comes on, brings that puddle back to life, you'll dab in your filler rod, and then the pulse comes off, and it's just a process. Really, the pulse sets the rhythm for the weld, because you're only gonna add filler rod when the pulse is on, and you move when it backs off to the low current. Let's set this up for pulses. You do it by pushing and holding the center knob to set up pulse control. I1 is our welding current, which we will control with the foot pedal. I2, sorry, set that back to 180. I2 is our resting current, and pulse hertz, that is gonna be our pulses per second. Now they represent it as hertz. I've always heard it as pulses per second, so you want, 1 pulse a second, 2 pulse a second, but let's just go ahead and leave it set at half. I think it's gonna be quite low. We're probably gonna have to turn that up, but let's just play with it and we'll learn together. Okay, with our coupon ready to go and pulse settings enabled at 0.5 hertz, let's see how many pulses a second that's gonna be. I suspect that's gonna be a little low for the speed I like to weld with, but it really comes down to how fast you can move. The idea, again, with pulse welding is to allow for minimal heat to be put into the part, but to achieve the weld you're looking for. Usually used on thinner materials, but it's not limited to thinner materials. Pulse welding isn't really something I do a lot of, because I'm usually welding between maybe 60 thou to 3/16, and I've just never really felt the need to use it, because I usually do most of the control with the foot pedal myself, but I know people have been asking about it. It really doesn't change much from regular AC TIG welding. The only idea is that the welder itself pulses to weld and then pulls back to a maintain current, holding the arc so that you can move, and then pulse to weld, pull back to maintain, you move. So you're only welding on the hits of current. So I'm just gonna draw an arc and hold it, and I wanna see the rhythm that the pulses are developing for me. I think it's gonna be a little low, and I'm gonna need to turn it up. Well, I'm not always right. That was actually a really good rhythm for me. Like I said, I don't do pulse welding a lot, so I'm used to setting my own rhythm or taking the time I need during a weld to move myself around. But for the first time really ever spending much time pulse welding, I'm pretty happy with that. It started off a little cool, but it really allows you to stack that bead in there. And I mean, I got a lot of heat in the part. Let's show you here. So you can see in here, again, you know, I'm not an expert at pulse welding, but it really allowed those beads to stack up nicely. And if we look at the backside, it was a little cool there, but it really started penetrating and coming into its own. So I'm really happy with that. Let's lay another bead down. Let's pick up the pulses and see if I can match. And again, the idea is you're only feeding material when it's at operating current. When it pulls back, you shouldn't be trying to feed anything in. You should be moving the torch and letting it pulse again. Okay, let's turn that up to 0.8 hertz.
I'd like to make a comment here that hertz is pulses per second. It's just another way of explaining it. So at 0.5, you're dealing with 1 pulse every 2 seconds or half a pulse a second. And at 1 hertz, it would be a pulse every second. So right now I am running at 0.8 pulses a second.
That's pretty good. That definitely picked up the pace for me. It sets the tone to move the torch, feed the rod, move the torch, feed the rod. I probably couldn't go much faster than that. Penetration is really nice here. I'll bring it in to show you. But I just don't feel the need to use those settings. I can do most of this with just controlling the foot pedal myself, but if this is a thing you want to look into, ow, that's hot. It's really just something you're gonna need to play with and find your own pace.
When you take a closer look at the coupons here for pulse settings, it really shows how much nicer using pulse can stack up the beads. By allowing you to travel with low current, you tend to not wash out the bead, and you can really stack it up. And when you look over to the backside, I was really impressed with the penetration as well. It seems that ramping up to that weld current really helps to dig in. So I was quite impressed actually using pulse, more than I thought.
All right, it's kind of fitting that I have 2 coupons left, and there was one thing I forgot to cover. Let's go through it right now, and that's gonna be like simulating a lack of gas flow, because that's probably gonna be one of the biggest things as an amateur welder that you're probably gonna fight, either contaminated gas or not having the correct gas flow, because that gas is extremely important to create a coverage over your part, because you want that arc and the molten aluminum to completely be in an inert environment, meaning no oxygen, no contaminants. It needs to happen inside an inert gas like argon. So I'm gonna prep these up, fire the welder back up, and let's dial that gas back to low and see what happens. Okay, I have got this gas turned down, and let's see what kind of quality of weld it gives us. Did you see that? Burnt right up. That was not enough gas flow at all. Okay, so there we go. Here I laid down a bead for comparison with approximately 12 to 15 CFH because I'm using a number 6 nozzle. In the center, I dialed that back, but it was next to nothing, and it burnt up the tungsten and spit it out and created a lot of black soot. So then I turned up the gas just a little bit more, and you can see what happens here. It melts the material, but it has no cleaning action really, because there's atmosphere pouring in, and it's just gonna create a completely sooty, it's just gross. So if you're getting welds that have a lot of soot in them, or just don't seem to have good arc control, or your tungsten is turning black and burning up, you probably have a gas issue and contaminants getting into your arc or weld zone. All right, well, I hope you've gotten enough information out of there to get out and start practicing some of this yourself. It's really not that hard. It just takes some time and experience. Don't be worried about screwing anything up. Tungstens aren't that expensive. Get yourself a good consumable kit. You're really not gonna hurt the machine itself. The biggest thing, the biggest takeaway in this video, I hope you will realize, is cleanliness. Aluminum needs to be clean, clean, and clean. Have a dedicated wire brush, wipe down with acetone, use a clean pair of gloves. If you can do all that prep well, you're setting yourself up for success. Everything else is just gonna be playing with settings, getting comfortable, which is probably number 2, being comfortable. Yeah, I think that's about it. If you wanna see any other aspects of this that I forgot to cover, I think I covered most things. Just drop a comment. I'm always up for doing a follow-up video, and yeah, get out there and play. That's all any of this is, and you'll get better, trust me. I hope you enjoyed that, and we'll see you in the next one.